All right, Matt. So if you want to go ahead and introduce Lior, and then we'll go ahead and get started.
Great. Thanks, Matt. Yeah, so we've got Lior joining us from the Israel Institute of Technology. And Lior's been part of a number of prestigious institutions and has most recently just finished a stint at doing as a postdoc at, that was at Stanford, correct?
That's
Yeah,
correct.
yeah, excellent. And he's worked with on um, ice in the inner solar system, all the way through dunes and machine learning on Mars. Won a number of prestigious awards, including the William Shatner Master Scholarship in
That's very true. Yeah.
2014, which I found, yeah, quite. I didn't have that one on my bingo card, but yeah. Why don't you take it away, Lior? Thank you.
Thank
Thanks
you,
for joining
Matt.
us.
Yeah, and thank you so much for inviting me to speak today. As Matt said, I'm currently, I've just recently started as an assistant professor at the Technion, which is Israel's Institute of Technology. I've finished my postdoc at Stanford maybe 6 months ago. And before that, I did my PhD at UCLA, where I've mostly worked about problems related to impact cratering on the moon and the accumulation of ice near its pole. And then in my postdoc, I've worked with Mathieu Lapotre on trying to characterize Mars's atmosphere and environment by studying the morphology of dunes and specifically of Barcan dunes. And in this process, we've stumbled across this interesting problem, which I'm going to tell you about, which we're able to kind of shed new light on by measuring a large number of Barcan dunes, in this case, on Mars, and understanding some or the relationship between the sizes of those dunes and the atmosphere. So, as you all know, this planet needs no further introduction. This is Mars, and what's very apparent in this picture of Mars is, of course, its north polar ice cap. When you zoom on this ice cap here, and when we zoom in on this ice cap, we see that it's surrounded by this black substance. And in 1979, a little before that, when the Viking spacecraft got to Mars, it noticed that this black substance is not at all coherent. It's actually composed of many dunes. In this image, we're seeing crescentic Barcan dunes, the form when the winds are more or less unimodal and the sand supply is limited, right? So I don't mean to say that in this entire cloud of this entire erg, sea sand is composed of Barcan dunes, but there are a lot of Barcan dunes in this sea sand, dark sea sand of Mars. Now, the existence of Barcan dunes on Mars was a pretty big surprise these days because we didn't think the atmosphere of Mars was, or we thought it's too faint to support the formation and the evolution, of course, of dunes, let alone large dunes like we see here in this image. Those dunes are hundreds of meters long, pretty large. And very recently, as this really cool animation by Matt, who just introduced me, shows, dunes do not only exist on Mars, they're also very active. So it looks like the faint atmosphere of Mars is not only doesn't only support the formation of dunes, the modern atmosphere of Mars also supports their migration, their transport. So it looks like this apparently, allegedly, faint atmosphere can actually pick up grains of sediment and contribute to the growth and evolution of Barcan dunes. And for that reason, for the fact that dunes are still active today on Mars, we can use them, like we do on Earth, to understand the surface conditions, the environmental conditions on the planet. So here I give a few examples of biology and vegetation and sand supply and sediment grain size. All those, of course, affect the morphology of dunes. In the right-hand side column, we see barcanoidal dunes on top, bark and barcanoidal dunes, and then linear dunes in the center, and the big star dune that forms when there's ample sand supply and the wind comes from multiple directions. All those features can be traced back to the conditions of the environment that formed them. So dunes of Mars are not only interesting because of the physics of dune formation, to understand the physics of dune formation on Mars, because again, this what used to be a big conundrum, why do dunes even form and migrate on Mars? They're also very useful and sensitive proxies to investigate its present, modern, and also past environmental conditions. We know those dunes are thousands, maybe tens of thousands of years old, and they can help us gain or shed light into environmental conditions in the recent past. And if we look at fossilized sediment, eolian bed forms, and even look even further into Mars's past, and then maybe understand something about its atmosphere. And before we begin, I want to extend an apology. The introduction of this talk is going to be slightly longer than usual, than at least my usual talks. And this is because, as this cute cartoon shows, the physics of sand are complicated. And the story begins on Earth, actually, where we see two clear modes of eolian transport. So we see what we call impact ripples on scales of between a centimeter, maybe a few centimeters, and we see dunes on scales of meters and larger. The smallest dunes, I think, are maybe 5, maybe 10 meters on Earth, something like that, maybe a little bit smaller than 10 meters. Well, we see those two distinct modes of eolian transport, or bed forms formed by eolian transport. And how do those bed forms form? Well, the wind, of course, is blowing across an erodible sediment, erodible bed of sediment, and then it takes those sediment grains, and because of it applies stress on the bed, it moves those grains of sediment. So it can move them through creep by making them crawl along the sediment bed, and can also cause them to hop, to saltate on the surface. It can entertain grains of sediment in the air. Those grains of sediment impact the surface, splash, release more other grains of sediment. And this process repeats itself until the air becomes, or the wind becomes saturated or filled with grains of sediment. And of course, the process of saltation can only occur when the wind stress is greater than some threshold, than some resisting force that prevents from those grains from leaving the surface. Now, we talked about two distinct modes of dune or eolian bed form formation. The first is those impact ripples. Those form by impact splashing. Essentially, the grains of sediment that hop on the surface and release other grains are protected by small mounds on the bed itself, right? If a small mound forms on the bed, the mound protects its right-hand side, in this case, its downwind side, from impacts. So we get net erosion on one side of the bed and net accumulation, because there's no splashing, on the other side of the bed. This causes this ripple, migrating ripples to form on the surface. However, dunes form by a different mechanism of hydrodynamic instability, which I'm going to get into in a couple of slides. But for now, I'll just say that when winds blow up those little mounds, the pressure contours, the isobars, get compressed, and because the wind that's close to the surface tends to follow the surface itself, we get this kind of a Bernoulli effect, which causes wind speed up at the top of the dune. And I'll talk about why it's an instability process in a second. But before that, here's a really cute or nice picture that I took in the Great Sand Dunes National Park here in Colorado. We can see ripples on the left-hand side. We can see saltation. I'm not sure if you can see that, but here there's sediment grains ejected from the crest of this dune. You can also see a video of the same process. This is during a storm at the same national park during a conference, and you can really see waves of grains carried away by the wind. And to continue this introduction, it's very important that we introduce or define the concept of the saturation length. So imagine there's a bed of erodible sediment and the wind is blowing across this erodible bed. It takes time for the wind to pick up all those particles, all those sand grains, right? It doesn't immediately pick up all those grains or entertain all of those grains. And the siltation splashing mechanism causes the amount of sand grains in the wind to increase with time and, of course, distance. So it takes time for the wind to pick up grains, cause them to siltate, cause those grains to splash other grains, which are then entertained by the wind and cause more splashing. So you wouldn't be surprised that the sand flux, the amount of the flux of sediment grains in the wind, increases with time and distance. However, it might be a little bit surprising that this sand flux comes to some saturation after some distance or some time. And the reason for the saturation is because every time a particle impacts the erodible bed, it loses momentum. And every time more particles are splashed into the air, they of course increase the mass of grains in the entertained by the wind, which negates the stress applied by the wind on the erodible bed. So we get this basically balance between the stress the wind applies on the bed and the fact that it's more difficult to carry more sand grains in the wind with time and or distance. And this distance between the beginning of the erodible bed and this saturation, the point of saturation, is called the saturation length. And I think the saturation length is a really good way of understanding why dunes grow by hydrodynamic instability. What do I mean by that? So we said before that there's the saturation length that separates the maximum bed shear stress in this blue line and the maximum transport rate. So the transport rate is separated because it takes time for the wind to pick up those grains, right? So it's separated by the saturation length. And then we can also define another distance, which is the distance between the maximum bed shear stress and the crest of the dune, the peak of the dune here. Call this distance, in this case, delta T. At least the Rand Vinent in 2019 called it delta T. And when this delta T is greater than the saturation length, then grains would tend to be deposited around or on the dune crest, leading to increasing the size of the dune, which would cause, of course, which would cause this saturation length to increase further and cause a further increase of the size of the dune. And this is what I mean that dunes grow by instability. That the small instability can there's a feedback mechanism. It causes small instabilities to grow into larger dunes. So let's go back to this modes diagram that I just showed you before. Now we understand how dunes form and how impact ripples form and why they're separated, why impact ripples have a different mechanism, formation mechanism to dunes. And when the first high-resolution imagery spacecraft got to Mars, we expected to see more or less the same picture, right? We've seen in those Viking images, we've seen dunes exist, and they have more or less the same size as dunes on Earth. So we should probably expect to see the same more or less picture. Of course, depending on the resolution of the instrument, we should expect to see impact ripples, should expect to see dunes. And we more or less did. I'm saying more or less because I'm going to correct this statement in a few slides. But what we saw are ripples, the size of a meter, maybe up to 10 meters, or something like that. And then dunes that on average, not just on average, that the minimum size of dune was much greater, about 7 to 10 times greater than what we see on Earth. So the smallest dunes on Mars are about 70, 80 meters long, more or less, which is about almost 10 times greater than the smallest dunes on Earth. So we see those ripples and then a separate mode of dunes. And this didn't really surprise anyone because, okay, maybe the faint atmosphere of Mars causes those impact ripples to just grow bigger than what they would grow on Earth. And we're just, this drop-off that we see on this side is just limited by the resolution. However, when the first rover images of the Bagnall dune field, in this case, came from Mars, we saw, to our surprise, a third mode of transport. So let me explain this slightly maybe confusing image, if you haven't seen it before. So we have the dune. This is the big pile of sand, dark sand that we see here in the picture. This is the dune. And then we see large ripple crests that are kind of, whose crests face us. So they go from kind of from the screen or in the direction of kind of the deck direction, if you will, from the screen into towards us. So we can see those crests, and they're separated by the 1 meter. These are the same ripples that I've shown you before. However, superimposed on those large ripples, we see smaller ripples, right? We see them all across the surface, which look a lot like the impact ripples that we see on Earth. And this was really confusing, because now we know impact ripples exist on Mars. So we see impact ripples, the same size on Mars, the same size we see on Earth. We see a separation. We see a clear separation between them and those large ripples that we saw from orbit. And then we see another separation, another mode of dunes. So we see 3 modes of, or trimodal size distribution, 3 modes of eolian bed forms. It's very confusing in 2016. And what are those meter scale ripples, right? That's a good question. So could they just be large impact ripples like we said before? Well, no, because why would they coexist with the smaller impact ripples? And specifically, why would they be separated? Why would the size of large ripples be separated from small ripples? If they were just the same, if small ripples would just transition, grow into large ripples with time, then we should see all the wavelengths in between small and large, centimeters and meters, but we don't. See a separation. Could they just be coarse-grained ripples? We see coarse-grained ripples on Earth. Coarse-grained ripples form when the sediment, when the the distribution of the sizes of the sediment grains is bimodal. So we see both large and small grains, and the large grains armor the crests of those ripples and prevent them or protect them from being eroded in the same splashing process that we saw before. So could they just be coarse-grained ripples? Well, no, probably not, because when we look at images, we see that the sand is well sorted on Mars. So it doesn't look like the sand, as you see in this picture, it doesn't look like the sand has a bimodal size. The sediment grains have a bimodal size distribution. And then in 2016, Mathieu Lapatre and colleagues, Mathieu was my postdoc advisor, as I mentioned before, suggested that. They said, okay, maybe because those large Martian ripples look a lot, morphologically, look a lot like subaqueous ripples on Earth, maybe like subaqueous ripples, they form from the same hydrodynamic instability as subaqueous ripples and dunes. So those large Martian ripples are something we do not see on Earth. And the reason for that is the higher kinematic viscosity of Mars's atmosphere, essentially. The fact that the density is lower, the kinematic viscosity is higher. So the kinematic viscosity, just to refresh your memory, is the ratio between the dynamic viscosity and the density. Now, if we plot subaqueous ripples on Earth, if we can do experiments in the lab, and we can also analyze observations, and we plot on the y-axis the dimensional wavelength, which is basically, you can think about it like the Reynolds number at the scale of the bed form, lambda star, which is just basically the scale of the bed form times the shear stress velocity of the wind, of the fluid, divided by the viscosity. And so this is on the y-axis. And on the x-axis, we have the Schiltz parameter, which is basically a parameter that determines the ratio between the stress and the weight, the stress of the wind, of the fluid, and the weight of the particle, of the grain. And then the Reynolds number at the grain, the particle scale. And when we plot those two, we get a clear relationship between the dimensional, the scaled, or the Reynolds number, the bedform scale, and this product of the square root of the Schiltz number and the particle Reynolds number. That you can see all those subaqueous ripples fall on the same line. And Martian ripples also fall on the same line as subaqueous ripples, as dictated by theory, as if they are really formed by hydrodynamic instability, like terrestrial subaqueous ripples. So could drag ripples, could those large Martian ripples just be drag ripples or small dunes formed by Mars's faint atmosphere? Well, no, because we know that dunes on Earth, at least small dunes on Earth, grow by instability. So if those ripples are indeed formed by hydrodynamic instability, why don't they grow into dunes? They should start small, and we shouldn't see a separation between dunes and large ripples. We should just see a continuum. We should see those large ripples slowly transform into dunes. So why don't we? And then the solution to this problem, potentially, came from experiments that were done in the 80s, and then a revised model presented by Orencio Duran-Vinent and others just a few years ago. And they said, well, we know that for a hydrodynamically smooth atmosphere, like Mars's atmosphere, or for hydrodynamically smooth conditions, this delta T is this distance between the peak shear stress and the crest of the dune, of the bed form, depends on turbulence within the boundary layer, which I'm not really going to go into, but basically it's related to that. And if the conditions of Mars, because the atmosphere is hydrodynamically smooth, if the conditions are different, it may explain why we see a gap between ripples and dunes. In those experiments found that for specific conditions, there's a range where no bed forms can grow. Basically, this instability that I've just mentioned stops. So if those subaqueous ripples and potentially large Mars ripples are the same, formed by the same hydrodynamic instability, they should stop growing where these experiments predict, because delta T just becomes larger than the saturation length, which implies no growth. And how can we test this hypothesis, this model, if it works on Mars? Well, we can measure the atmospheric density, which, as I said, is a measure of the viscosity. The kinematic viscosity, again, is the ratio between the dynamic viscosity and the density. So density is on the denominator. So on the x-axis, we can put density. And on the y-axis, we can put the bedform dimension. And those should be related based on those theoretical laws and also semi-empirical laws and measurements that were conducted on Mars, both by Mathieu Lapotre in 2016 and also more recently by David Vast. And we see that indeed large ripples on the bottom of this plot do obey some correlation between the density, the atmospheric density, the fluid density, and the size of the ripples. They increase with decreasing atmospheric density. Above them, we should have this forbidden gap that we just talked about, right? That was predicted by those Henretti experiments, the Henretti gap. I'm going to refer to it as the Henretti gap. So this gap stops those ripples from growing further, potentially. And if this is true, then all the dunes on Mars should sit on top of this gap. It should be separated by those large ripples. And if we're lucky enough, they should also obey the same correlation, the same proportionality between the density and bedform dimension, because they're formed by the same mechanism. And this mechanism, again, is hydrodynamic instability. So basically, what we should do to confirm or refute this hypothesis is to measure enough dunes on Mars and to measure the size of the smallest, the average, or the smallest size, the average of the smallest size dunes on Mars, or something like that. Measure many, many small dunes on Mars and see, because they're representative of the incipient size of transverse dunes on Mars. And then try and correlate that with atmospheric density and hope to reconstruct the graph, the plot that I just showed you, that are related to the atmospheric density and the kinematic viscosity of Mars. And one way to do it, of course, there are many ways to measure things. One can do this manually. However, to get a good statistical sample, we need many, many measurements. And expecting or I think that expecting a person to measure quickly many hundreds of thousands, if not a million, Barkan dunes on Mars is a big ask. And this is because, of course, manual measurements take a lot of time. And I like to give this example that the famous, the most, I think, detailed crater catalog of craters on the Martian and the lunar surface took Stuart Robbins almost a decade to complete, which is a very impressive amount of work. However, it's also very difficult for humans. However, for computers, this task, especially if we know what we're doing, is slightly, I'd say, easier, can save us a lot of time. And just to really quickly, I'm sure you all know what machine learning, and of course, you all know what deep learning is, given the popularity of ChatGPT, right? In the recent, what, year or a few months, I think. We've probably all used ChatGPT, even just to see what it's about. And I really want to briefly touch on what deep learning is really. And I'm going to do it using this really simple example. So let's say we have a cloud of points. We have two types of points: the red, the orange, and the blue points. They're separated from one another. We as people can see that they're separated. However, can we ask the computer to find a line, just one line, that would separate those two groups of points? Well, that's pretty difficult, right? Because any line that you draw on this picture, this or that, would not be able to separate those two groups of points. However, if you go back to basic classes in physics that you probably took when you, or physics or whatever, any other science, math maybe, during your undergraduate degree, you probably remember coordinate transformation. Because when we apply coordinate transformation on these clouds of points, in this case polar coordinates, we find that they're pretty easily separable by a single line. And this is exactly, or more or less, this is exactly what the goal of course, the simplification, but what deep learning algorithms do. They take a complicated or a non-linear problem, and they try to linearize it. They try to what we call abstract it, so that we could use our linear thinking, our linear models, to try and make sense of the data. And some of the best uses for deep learning algorithms are object detection, which is very useful, for example, in planetary science, in the geosciences, I think, as a field, because it could save us if we will learn how to really optimize those algorithms, and if we learn how to use their conclusions in the right way, we can really quickly and efficiently make sense of a lot of data and ask ourselves statistical questions like the one I'm asking in this talk. So the algorithm, the neural network I've used in this specific project is called MESC-RCNN. RCNN stands for Regional Convolutional Neural Network. CNN is a convolutional neural network, and again, I'm not really going to go into what is a convolutional neural network because I'm sure a lot of you already know. I will just say that I'll just briefly explain how MESC-RCNN works. So, given an image, we pass this image to the first box here, a convolutional neural network, also called the backbone of MESC-RCNN. And this convolutional neural network, as we said, it's very good at abstracting data, taking the image and figuring out what's important about the image. We call this, what's important in this image, the feature map that we see here. It extracts basically the most important features in the image. And then it takes this feature map and it passes it to an RPN, a region proposal network. All this region proposal network does, it takes random boxes in the image and tries to guess whether those boxes contain objects or not. That's all it does, basically. Let's say it draws a box around this thing here and it says, okay, does this thing contain an object, or is it just the background of the image? And the way this works is, of course, through optimization, through training. I'm going to talk about it in a few slides. And then this information, the feature map and the RPN, is passed to 3 loss functions. So a loss function, you can think about it like the loss function of the regression, the well-known loss function of regression, which basically minimizes the distance between a bunch of points and the line that passes through them, right? We just want to minimize the sum of the distances from all those points to the line. So those are other loss functions with other goals, other that's structured to give us other things. So the softmax loss function helps us classify the object, whether it's a bark and dune or a rabbit or whatever. And the bounding box loss function basically helps the network decide what is the size of the bounding box that surrounds the object that it just detected. And segmentation is the most important part of this neural network, because all it does is it tries to decide which pixel inside this bounding box belongs to the object and which doesn't belong to the object. And all of this process is, of course, done through training. And by training, I mean we take a lot of images and then we manually label them. This took us about 2 weeks. So we took about 1,000 images and we manually label all the bark and dunes in those images. We're very careful not to label anything else. And we're very careful to label just the bark and dunes or all the bark and dunes in the image to not confuse the model. And once we do this for this small training set of images, we can go ahead and train and optimize the neural network to find contours or masks of bark and dunes in images it hasn't seen before. And a question that I often get is why Barkhans? Why not use other dunes to do everything you're doing? Well, in this case, Barkhans are transverse, and the theory for the relationship between the properties of the atmosphere of the fluid and transverse dunes is pretty solid. So this is a plus. They're isolated, which means labeling them for humans and computers alike is more easy, right? Is easier than it is when labeling or contouring continuous objects like linear dunes. When does a linear dune start and when does it begin? It's kind of a philosophical question almost. However, for isolated objects, it's very easy to label and later detect them. Bark dunes also have a distinct shape. So they're pretty dissimilar to other morphological bed forms of Mars, right? There are not a lot of things that look like moonlets, like crescents on Mars. And the morphometrics of bark and dunes are also very revealing. So except for the question that I've raised here, whether there's a relationship between large ripples and those incipient dunes, we can learn other things about Mars's atmosphere just by looking at the shape, the morphology of bark and dunes. So because of all those reasons, bark and dunes are very useful for our investigation. Okay, so we said we trained the model, we gave the model a lot of examples. How do we test it? How do we know machine learning, the machine learning approach actually works and it can actually detect objects in the images? So I think the first thing to note is that it's important, in my opinion, to separate analysis from detection. You can, of course, use neural networks to analyze that. You can give neural networks images and train them, for example, to find the wind direction or to measure the size of incipient dunes or whatever you want to measure in the image. All you do is you train on pairs of images and data. However, deep learning models, those neural networks are like black boxes. We would never know how the model got to the conclusion it got to. If, for example, for a specific dune, we measure a size different than what we expected, we would never know how to debug this because again, it's a black box. The processes, there's a whole field of research called interpretable machine learning that focuses on understanding that. So in this project, and this is again, it's just my philosophy. It's not the actual truth. We only focused on contouring, on masking dunes, just on the process of detecting, which is very difficult for humans and very easy for a computer. And then wrote further code, as I'm going to explain later, to analyze the morphology. So how do we check that the detection, the masking process actually worked? Well, neural networks have those knobs and handles we call hyperparameters. Those are different than the parameters that are optimized through the training process. And those knobs and handles, when we change them, for example, we can change the backbone, the complexity of the model. So this is equivalent to, for example, when you have a set of points, this is equivalent to choosing the power of the polynomial you're going to fit to these set of points. You can choose a polynomial of order 1000, or you can choose the first degree polynomial, right? So choosing the backbone of the neural network just increases the number of parameters and the complexity. Choosing the wrong backbone can lead to overfitting or underfitting. I'm not really going to go into that. However, there are a lot of similar properties that we can tweak and change until we get the accuracy that we're happy with. And of course, we can always train the model further, and of course, we can always tweak those handles, knobs and handles further until we get higher accuracy. However, of course, we should stop at some point, because this is a never-ending process, and there's always a competition of who has the best model. And I think this is not very helpful in science. We want to know what accuracy we need to answer a question. That's the only thing that interests us. We don't care about making the best possible model. Maybe we do, but not in this investigation. We just want to get a good enough model that would help us understand the question. And in this case, we got to an MAP, a mean average precision, which is a factor that takes in, or a parameter, or a number that takes into account the number of false positives and true positives and false negatives and true negatives of the image, takes all those into account. And by comparing the bounding box of the detected to the ground truth bounding box in a separate test data set, you can compute this number, and this is more or less the accuracy of the model. Again, I'm not really going to those fine details here. I'll be happy to take questions about it, but the model is about 78 or almost 80% good at detecting dunes. And this, in when we did our analysis, it was good enough for us to basically obtain a statistically significant sample of dunes on Mars and answer the questions that we wanted to ask. And another example of how the model performs, left-hand side, we have a picture of an image of Barkan dunes. Around the center, we have an image of a traditional detection algorithm. This is called the Canny edge detection algorithm. It works by differentiating the picture in 2 dimensions, and it's doing all these other neat tricks, which I'm not going to talk about. We can see that it more or less can identify the outlines of Barkan dunes here in the center. However, it also returns a lot of false positives, which is not good for us. We don't want to detect all those other objects in the image. And on the right-hand side, you can see how the CNN did compared to this. And it did a lot better. First of all, there are almost no false positives. There's just one false positive, which looks like the backside of a dune. So, I couldn't really fault the algorithm for that. But most of those dunes are correctly detected in the image in this specific example. And we said that we try to minimize the involvement of the black box machine learning, deep learning algorithm. So the next step is to not manually, but using writing code to automatically measure the morphology or characterize the morphology of Barkan dunes. So for example, we can detect the locations of the slip faces by finding the convexity defect along the contour of the dune, right? We can detect the horns by looking at the intersection between the contour and the convex hull of the shape. We detect the tail as the point furthest away from the horns in the bottom part, in the south side of the dune. We also estimate the migration direction of a dune and of the image, right? Like you see here in this windrows, just based on the normal to the slip face, accounting for the asymmetry and all those other things that I haven't really explained. But we can write an algorithm that you can also check that, given the contour of dune, gives us what is the properties, what is the morphology of this dune. So first we said that we have to first make sure that dunes on Earth and Mars follow the same physical laws, and we can do that by testing the scaling laws of dunes on Earth and Mars. And we see 2 interesting things here. Let's focus on this panel here. I'm not really going to talk about all the panels. Let's just talk about width versus length here. So we see 2 interesting things. First, we do see, like those models predict, that dunes on Earth are the size of the smallest dunes, the incipient dunes on Earth, measured by all those studies that you see here on the right, measured manually with all those studies, are smaller than the smallest dunes on Mars, right? So we see this difference in the size of the incipient dunes on Earth and Mars. Do we see the advantage and the disadvantage of the machine learning and this automatic method? We haven't manually measured each and every data point here. So this leads to higher scatter compared to manual measurement, right? However, we also have a lot more points. So the existence of all those points reduces, of course, the statistical uncertainty of the data. So there are pros and cons in this automatic method. Here's a kind of deviate from the topic to show these really neat maps of dune morphology near the poles of Mars. So this is the north polar arc of Mars, and we can map, for example, trends in the ratio between dune length and dune width. So we see the dunes closer to the ice cap are slightly wider than they're longer. They're redder, right? So it's the other way around, sorry, slightly longer than they're wider. And we can see the dunes in the Olympia Ande are the most voluminous. And also we see the same increasing volume near Escorial. I might be able to kind of explain why we think we see those increase in volumes. This is probably related to convergence zones. We'll talk about, hopefully I'll have time to talk about it later. And then we can also map asymmetry, for example. So we can really do this data science type analysis by looking at all those dunes near the pole and globally on Mars. And let's go back to the hypothesis that we raised just maybe 20 slides ago, right? So we said, okay, we have the ripples plotted on the bottom of this plot of density versus bedform dimension. We have this Hanratty anomaly, Hanratty gap, the hydrodynamic anomaly, which here is computed from models, right? This is just computed from models. We can't really measure it, but we know more or less what's the Reynolds number at the bedform scale. We know what's based on the grain size, the fluid, the shear velocity. So if you're right, if we're correct, the dunes should appear here, right, near the top of the plot, separated from the ripples, and also should follow the same scaling as large ripples, and they do. When we take all those dunes, we see they follow more or less the same. So the scaling, the theoretical scaling should be minus 2/3. A subsample of ripples measured on Mars has a power of minus 0.63. Dunes have a power of minus 0.66, so even closer to this theoretical scaling than even those restricted statistical samples of ripples on Mars. But we see, nevertheless, that they follow the same scaling and also separated by this hydrodynamic anomaly, like predicted by this model by Durand-Vinet. And we can ask ourselves, maybe this is because we don't know the properties of the Hanratty gap, because we don't know the properties of the atmosphere. So we tried different properties, and we always ended up with the same result, that the gap is in between those population of dunes and ripples. It looks like it's very tightly and very well separates those two populations, as the theory predicts. So let's go back to our diagram from before. We said large ripples on Mars cannot be drag ripples or subaqueous or similar to subaqueous ripples, because we know they must grow by instability. Yes, these results show that what happens is that those drag ripples cannot grow into larger dunes because the Hanratty gap prevents them from crossing the border into those large dunes, or prevents them from increasing in size, growing in size into becoming large dunes, as theory predicts. And I think that, as pointed out by others, more important people than me, this demonstrates that we should change the Earth-centric view of eolian processes, and maybe take into account this Durand-Vinet model that I just showed, that talks about how the atmosphere and the atmospheric conditions and the properties of the atmosphere affect the size of eolian bedforms. This is an This is a picture from dunes on a comet, right, from P67. And just to conclude, we use neural network to automatically characterize bark and dunes of Mars. We infer dunes morphometrics from the detected outlines, and then we follow to measure the morphology of those dunes from those outlines using an interpretable method. So code that we wrote that actually takes the contour and you can track and follow each and every step in the way and understand really what this code did. So it takes the contour and returns the morphometrics of the dune. And we see that dunes and large ripples follow the same scaling laws as theoretically predicted for subaqueous ripples. And the dunes and large ripples are separated by a forbidden zone for dune growth as predicted by those experiments in the 80s by Henretti. And this, of course, bolsters the hypothesis that large ripples are formed from the same hydrodynamic instability as dunes. And because I have a couple more minutes left, just want to show you another neat result of this project. We can also, as I said before, try to learn something about the global migration rate of dunes of Mars, right? And maybe compare this to our predictions from GCMs. So we have GCMs of Mars that compute the global circulation of the planet, and we can try and relate those winds, those global circulation models, to how to the directions of migrations of dunes across the surface. And to do that, we can look at dunes at different seasons in the year, as I'm showing here. Of course, the directions and the magnitude of the migration can be different in different times of the year. And maybe this rose diagram that you see here, the white arrow shows maybe the average migration direction, more or less. Or sorry, not the green arrow here shows more or less the direction of average, and white is the average migration actually measured by our CNN. And then we can make a map of how would dunes or how does the global circulation of Mars looks in the eyes of dunes, and we see a lot of interesting things already. So we see that in high latitudes we see this zonal flow, right? And then we see this the northerly, the flow to the south, the northerly winds or the southerly migration direction. So dunes migrate to the south in kind of mid latitudes below 45. And this is a really interesting map that can help us by comparing this map to the global circulation shown here in those contours, in those streamlines in the background. We can learn a lot about how dunes react, or how dunes respond. This is the word I was looking for. How dunes respond to Mars's global circulation, and maybe understand more not only about how dunes and climate kind of respond to one another, but also potentially it will help us understand, infer previous measurements and maybe even fossilized measurements of dunes and other eolian landforms, and from them understand what were the climatic conditions of Mars tens of thousands of years ago, and maybe even before that, maybe even millions and billions of years ago. Thank you. I'd be happy to take your questions.
All right, great. Thank you, Lior. Yeah, I definitely have questions for you, and I think we've had previous conversations, but I want to open it up to anyone else if they have a burning questions, and otherwise I'll jump in. So I guess with the forbidden gap, and you had some assumptions about particle size, and we do see bedforms in that gap, and we kind of, I don't know, we call them transverse eolian ridges and tars. Yeah, I like that plot with the tars there. So yeah, maybe talk a little about that, about what are the factors, the assumptions. Those probably have particle sizes greater than 125 microns. How you could tweak your model and think about the bedforms that exist in that dimension.
So I think to answer your question, I think the most important thing is to really understand what tars are, really. I think we don't have a very good understanding of what modern tars represent. I agree with you that some of those data points kind of exceed into this forbidden zone, especially in this model that we see here. However, just because, like you said, we are uncertain of the real width of the hydrodynamic anomaly, like I've shown here, I think testing it with other bed forms and testing with other parameters could help us understand why tars can actually exceed into this anomaly. But for now, because I don't think we, as you said, know for certain there's probably a difference in the grain size distribution across the surface of Mars. And we're not entirely sure that using, like I'm showing here, using the fluid threshold shear velocity as the U star here, as the shear velocity is the correct value here. So I think this just represents the uncertainty in those measurements. The fact that sometimes tar kind of exceed into this forbidden zone.
You have any other questions? I guess, yeah, maybe just kind of a general topic. You had a couple things on your research statement about different projects that you might would be interested in collaborating with other PSI scientists. Maybe, yeah, I don't know if you want to throw you under the bus to talk about those or
Yeah, I'd be happy to. Matt, maybe we should you should introduce the topic you're leading in this case. But I think this data set, I'll say it like that. I think this data set that we've just finished accumulating just shows the tip of the iceberg in our possibility in our it can open up more possibilities to understand the modern and recent climate of Mars. And specifically, I think one of the more interesting questions, which I haven't really talked about in this talk, which is already too long, is the relationship between local conditions caused by, for example, topography deflecting winds and winds caused by katabatic winds caused by local variations in temperature, just by slope winds, just by local conditions. How are those related, for example, to, I'm going to go back to my last slide. How are those related to the global circulation of Mars? How do those affect the migration of dunes? How big or deep or rough must the surface be or landform be to affect the migration of dune? And how does the combination of global circulation and local circulation affect the migration of dunes? And I think, again, this goes back to our ability to interpret fossilized sediments. If we don't know how topography affects the formation and the migration of those sediments, how can we really interpret those really old sediments and understand something about Mars's past climate? So I think understanding the mesoscale versus the global scale and how does this data set respond to those two scales, I think it's something I'm collaborating with you on, and I'm hoping to continue understanding. And I did talk about my collaboration with Norbert, who I see is on the call as well, trying to understand how this is on a different planet. This is on the moon, not a planet, planetary body. Trying to understand, for example, how does meteorite impacts affect the formation and the stability of ice near the poles. And also how they affect the turnover rate of the surface, which again can help us understand a lot of modern geologic processes on the surface of the moon. So
Excellent.
those two of the things I've talked about, and I thought I'd mention. Yeah.
Yeah, I think we're getting close to the end of the hour, and I don't want to. I know Kirby was on earlier, but it looks like he had to jump off for maybe another telecom. But he's got expanded interests in bedforms and regolith production. So that's another area where you might, if you ever run into him, you might be able to talk over some of those topics. But with that, I guess we'll thank you for coming on and everyone for calling in. And it was an excellent talk. And yeah, absolutely. And just to let everyone else know that you're thinking about visiting the Lakewood office in PSI, Colorado. And so we'll look forward to coordinating with you on that, and we'll go from there.
Sounds great. Sounds great.
Awesome. Thank you, Lior. Well, thank you everyone for calling in.
Thank you, Matt.
Have
Thank
a great
you.
day. Yeah.
Bye.
Cheers.